you're right, there's a logic bug, and that's perfect. I mean, it's not fun, but yeah, of course it's fixable. I mean, I didn't release any of those without having at least one solution that would actually pass all of the tests in the grader. So, so I know it's possible, even if it's a little challenging or difficult. Size of the class keeps shrinking. It's okay. I was thinking of bringing donuts one day. Stopping by Lucky's Donuts and bringing donuts in. And as the class gets smaller and smaller, that gets cheaper and cheaper for me to do. So this is perfect. Absolutely perfect. Well, it's time to start. This is actually going to be a little lighter lecture than most of the lectures have been up to this point. And that's because on Thursday, I'm going to start slapping your head around with distributed consensus. We're going to start with one of the oldest of the consensus algorithms. We're going to be talking about what's called quorum replication, and then we're going to move into Paxos, and then we're going to move into U-stamped replication, which is also known as Raft, same protocol. And that's going to bring us right up to the reading break, and then you're going to get to go and do something unrelated and forget about this stuff, so that when you come back, 2 months later, all right, it'll only be a week later. It'll just feel like 2 months later. You'll have forgotten it all, which is great. And of course, the mouse isn't on whatchamacallit. So let me come back over here and physically move the mouse, which is this big glowing green thing, so I can see it. There we go. All right, usual logistics slide. So let's see, the Project 2 reports were returned last evening. Feedback is on Gradescope. People did fine. That's the first two projects. The reports aren't really very stressful. We are expecting a bit more in your Project 3 because Project 3 is more substantive. So you should have actually started to have to make things like design decisions. Why did I do things in a particular way? I've seen some good conversations on Discord. Discord seems to be pretty, well, reasonably active. I wouldn't call it pretty active, but reasonably active. We had some good conversations there. There's been a couple of conversations on Piazza as well. Piazza just feels like, I don't know, less interactive than Discord because it's less interactive than Discord. But they're both available. Let's see, don't forget that Project 3 is now, in fact, less than 1 week away, midnight next Monday. That way you won't. And then the project after that is an entire month later. All right, 4 weeks, but who's counting? And that way you have reading break. You shouldn't be feeling a huge amount of stress from this class for your reading break. I'm sure that you'll have other classes where people will be rushing things in right the Friday before, so you have plenty to keep you busy during reading week. Does anybody actually do reading during reading week, or do you just like go find someplace warm and sunny and sit on a beach? Or pretend that you're sitting on a beach because you sit in front of a picture of a beach, or you have a beach picture as your Zoom background. I have that too. It always makes people jealous. I'm like, I'm not actually there. Nothing else has changed there. For people who have taken the alternate paths, all of the alternate path 1 teams have private threads. There are questions for all of those people that need to be answered. I have one team that I posted things last week, and they have yet to respond. So I would strongly encourage you to check those out. We have the one person who picked the open source software project option, and they actually did great. So they have a grade on Canvas for that. I have office hours this afternoon. Those are Zoom office hours. And I actually have a couple of slides about Project 3 that I'll use during the Zoom office hours. There's not a lot to say about Project 3. There's a little bit of complexity to it, but it's definitely a step up from Project 2. But there's already multiple people who have actually submitted fully passing Project 3s. No pressure. Lots of different papers that you can look into if you're interested in the topics for today's lecture. I have drawn a number of these conversations, and I will actually, you don't have to read any of these, but I will actually refer to some of the things that we learned from these various papers. There's nothing that stands out hugely in this list. Corfu is an interesting distributed log. Now I should run over there and block him and just really confuse him. It is a very interesting implementation of a distributed shared log, and it's about 10 years old now, that paper. Serverless network file systems is much older, but in fact, many of the principles that are involved in building a peer-to-peer network file system look an awful lot like the things that we do with logs. And so what you see is that these later log papers end up referring back to this distributed serverless network file system paper. And we haven't stopped building serverless network file systems either. The interplanetary file system, for example, is effectively a serverless network file system built on top of a blockchain. So now we add Byzantine failure to our analysis there. Paper on distributed logging for transaction processing. This is actually, yes, that's a really old paper. And one of the reasons I included it is because I know two of the authors on the paper because I worked with them at a company that did two things: distributed file systems and distributed online transaction processing. I worked on the file system side, and I knew a lot of people on the distributed online transaction processing side. And then I was like, oh, this looks interesting. And Engrave Chain is a blockchain-based tamper-proof distributed log system. Now, so this is kind of that interesting question on steroids. How do I actually start building a distributed log where I can actually validate the information that's put in it so that it can't be tampered with? And they go a little bit further. They actually do use an encryption scheme. So you can have a validatable log on a blockchain with data that's actually been encrypted. So you're not even necessarily leaking a lot of information there. And their concern was things, and I'll talk a little about this a little bit more. Their concern were things like personal medical information and credit card information, and basically things that involve money and things that involve personal health information are very sensitive. I once worked with a guy who actually did consulting for the US Internal Revenue Service, and they had a security classification that made almost everything the military used look like child's play. It was insane. And that's because it involved money. Almost anything that involves money will end up touching distributed systems because the people who are willing to pay the kind of costs associated with building redundant, fault-tolerant, Byzantine fault-tolerant systems are the people who are touching money or something that has real economic value. And then Ponzi was an interesting tool. I think that was actually the tool I was mentioning to you, where they built a log analysis tool. And they used log analysis after the fact in order to do failure analysis. So they're using distributed logs to look at the failures to try and extract what went wrong. Any questions at this point? Okay, so one of the things that I have seen as a common theme now, and I wanted to mention this, is when we are building our distributed systems, we cannot possibly plan for all of the failures that could ever occur. And just to do that, let's see, I have picked a very short, but hopefully slightly humorous link. And of course, I have no sound because I turned the sound off, so let me turn the sound on. This is much more fun with sound. If you've never seen this, it's a great movie. And there you go. I'll turn off the sound. And there you go. So, indeed, we cannot plan for all the possible failures. So one of the things I've seen in the conversations, even about Project 3, are, but what about if this happens? And the answer isn't you have to handle every possible failure. The answer is at some point you say, this is a failure I don't handle. It's okay to do that. The test itself says these are the cases we expect you to handle. So for instance, there's this interesting discussion about what happens when the primary fails and there's no backup. You cannot handle that case automatically. And what I find interesting is that people don't step back and say, why? What am I supposed to do in this case? So here I have this database that I've mutated to this particular state. The database, the one copy of the database that's available goes down. What am I supposed to do? Choose some other random server that's never actually done anything with that database and throw it into the mix? What happened to all the data that I put in the original database? What happens to the guarantees that I gave the client that said, I'm not going to roll backwards? I just rolled backwards to the beginning of time. This is when you actually have to go for manual intervention. So in the case of the Vogons destroying planet Earth, manual intervention is this crazy little dumpy Englishman going to find a planet of people who build planets. If you've never seen The Hitchhiker's Guide to the Galaxy, it's very British. If you like British humor, it's very funny. It's very weird, but Douglas Adams' writing in general is very weird. And yet, it's good enough that they've made, I first heard this as a radio play. Literally a radio play from BBC in, let's see, would have been the 1970s, mid-1970s. And they've done movies, and they've done TV versions of it, and the whole thing. So if you don't know the story, the basic story is that the Vogons are these nasty, ugly, horrible creatures who have atrocious poetry, and they are totally fixated on process, which of course is a whole British thing, right? That's why it's been in the planning office for 50 years and you didn't even bother to go look at it. It's like, I couldn't even get there. Doesn't matter to them. They blow the planet up. We have to recreate the planet because the people, well, the creatures that created planet Earth were trying to figure out the answer to life, the universe, and everything. Now, this is the humorous part about it, is that they blew up the planet 5 minutes before the answer was supposed to come out. And there's enough residual state in Arthur Dent's brain, the Englishman, that they're going to be able to reconstruct the planet and get the answer. And they do eventually get the answer. And you will hear me say this sometimes when people go, I have a question. I say, and the answer is 42. That's from this exact series. But the point here is, you have to do manual intervention. They go on this long adventure to go and find the people to rebuild the planet so they can finish and get the last 5 minutes of the computation. I think they called it Deep Blue. I think that was the name of the computer. The Earth was the computer they built. Okay, great. Do not solve every problem. You can never solve for the complete destruction of the Earth given our current set of technology. Give us 50 years and we'll either not care about it, or we will have facilities on other places that even if the Earth got blown up, it would be able to survive because we'll be on one of the 496 moons of Jupiter. What is it? Jupiter's up to 97 moons that we've discovered. It's a lot. And some of them look like they might even be sort of habitable. Very small number, but great. When we can put a data center on Io, then we can start worrying about the destruction of the Earth. Until then, don't worry about it. When your primary goes down and there's no backup server, you're stuck. You're dead. The best solution at that point is to keep the primary in the view and hope that it comes back up. If that doesn't happen, then someone with more authority than your little solution for this project has to come in and has to restore from backup tapes or whatever backup media you choose. Or you can reconstruct the entire database. I mean, I read the sysadmin subreddit, and it's absolutely hilarious when you read the things that are going on there and the fact that people have these whole distributed systems where they put single points of failure in them all the time because, of course, it costs a lot of money to maintain replicas. There was one this morning, a domain controller, which is a Windows Kerberos implementation that keeps distributed credentials. And Kerberos has been around for a long time. Domain controllers have been around for a long time. But of course, if you work for some small organization that isn't willing to buy redundant hardware, what you end up with is a 20-year-old domain controller that the hardware finally fails. And when that happens, do you know what happens to everything in the company or the organization? It stops. No one can log in. You can't authenticate. You can't talk to anything. No one knows who you are or what you are. And that's when you find out that the backups you've been making for years don't work. I mean, literally, the person who was describing this is funny. They went on eBay and purchased a piece of hardware that was end of life 5 years ago. And they had to get authorization to do that. Don't be that person. Manual intervention is necessary, but the reason we build distributed systems is because once we stand them up, we don't have those single points of failure. So when we have a steady state system where we have a primary and we bring a backup in, why is it that we don't allow the view server to tell the rest of the world that the backup is there before the primary says it's okay to do that? Why? Maybe it does have the consistent state of the primary, but what node in the system knows what the state of the backup is? It's not the view server. The view server is actually a very simple little configuration server. The only entity in this system that knows if the backup is in sync is the primary, and that is why you actually wait for the primary to acknowledge the view before you make the backup visible. When the primary tells the view server, yes, the backup can now is now visible. I acknowledge your proposed new view. Now the view server knows, okay, if the primary fails, now I have a legitimate backup. That legitimate backup can then become the primary and continue to give the guarantees that I gave my clients that they're not going to lose information. I now have my durability guaranteed. That's why we do it that way. That's why if there's a primary and no backup and the primary goes down, we don't set the primary to null because then we'd be back to like the initial state. And then we'd be like, okay, let's see. Anybody want to like step up to the plate with your empty database and just like start randomly serving nothing? You wrote a client expecting these guarantees. You didn't provide that guarantee. So either you're going to restore it from backup and you're going to get as close as possible so you manage to meet as many of your SLAs as you can. SLA, service level agreement. You'll hear this term a lot used in distributed systems. It means this is what I promised my customers. And if I don't give that to them, they're going to want their money back. Catastrophic things happen. We cannot prevent all catastrophes. Oh, and that that video is not in the slides that I posted. It's kind of hard to put a video in there, but I think I linked it into the Discord channel though, because it was so good when I found it. I was like, yes, this is exactly what I wanted. Let's talk about another failure. I'm trying to pick on people a little evenly. So I've picked on Azure, I've picked on Amazon, and now I'm going to pick on Google. I don't want you to feel like there's some superiority here, because all of these organizations have interesting, challenging problems. This one is interesting in that basically they detected and started correcting for it within 2 minutes, and the outage was still multiple hours long. And they don't ever really tell you how long it took to completely mop up the mess. So a little bit of network connectivity problem. It caused some degradation and disruption, which meant 33% of the compute engine packets to the compute engine were being lost. 33%, that's a lot. That means we got a lot of retransmission, which of course, what does that do? That spikes our load on our network, which causes other problems, blah, blah, blah. App Engine had a 23.2% decrease in requests per second. This is where things like SLAs start coming into play. And when you go look at the original Google post, I may not have put the link in there. If you go look at the original Google post about this, they actually have the bottom say, if your SLAs were violated, let us know and we'll give you a refund. It was nice of them to be very proactive about that. You can tell us if we owe you money. 50% of service configuration push workflows failed in the cloud endpoints. Up to 100% packet loss. Now, I'm actually going through their notes and where they say, well, it went from like 10% to 100%. And I'm like, 100% is the number I'm looking at and going, yeah, for some people, this is really bad. That was for their cloud interconnect. So the services that were running across their own cloud couldn't talk to each other. Ooh, that's kind of bad. They had their cloud VPN. Multiple gateways were unreachable. Well, that kind of sucks if you're trying to connect to your services. And of course, we all use VPNs because we want to make this part of our private network, not publicly available over the internet. So if we can't do that, we can't talk to our services. And that means that our organization is not getting its work done. So this is a big impact. And it's hours of people. And of course, it happens during the middle of the day. So it's hours of people in the middle of their productive work time, and this stuff happens. One of the things you will actually see when you look at real-world distributed systems is they often try to do these things at a time when it is minimally disruptive. But there's never a time when it's zero disruption. And when you start becoming global, there's never a time where it's minimally disruptive in any definition of minimal. So there's always disruption for someone and something. And there were 6 more impacted services there that I didn't even have space to list. And this is the TLDR version. And the cause. 2 normally benign misconfigurations, which means we've done this mistake before and nobody ever actually noticed. The network control plane jobs were configured to be stopped for this maintenance event, which is apparently something that doesn't happen very often. Okay, fine. And the cluster management software instances were included in these relatively rare maintenance events. So we have a couple of unusual events that just happen to come into conjunction and boom, bad things happen. This is one of the reasons why testing this stuff in advance is really difficult. Oh, if you want to test this, all you need is you just need an extra system on the side that's the same size, at least the same size as the thing you're testing. Okay, so I have a global, geo-replicated, distributed network of interconnected services spanning tens of thousands of machines across hundreds of data centers. I just need to build an extra one of those. How expensive could that be? So the reality is you're never going to have that test facility. And this is why you end up testing in production. You try to do smaller spot tests to check to see if the individual pieces work. But it's not the individual pieces that fail. It's when you put these things together that suddenly you have this interesting interaction that you never even imagined could happen. And then the maintenance event software initiator bug that allowed descheduling multiple independent software clusters at the same time. Oh, by the way, the clusters were geographically distributed. So we built geographical distribution so that a single outage of a single data center wouldn't take everything down. And we did it ourselves. Oh, gee, I have 2 feet. Let me use 2 guns to shoot at the same time through both of them. Boom. Their mitigations didn't work. The BGP routing stopped, and I was like on a YouTube video thing. So I was like, hey, I'm going to capture this one too, because this is, as soon as I read this, this is what I immediately thought of, and it didn't take very long to find this.
Go west next intersection. Oh no, intersection. Keep right on this track. And it is the yeah. Keep the road. And you did that scenic coast.
If you've never been to Maine, the old timers in Maine really do sound like that. This is and this exact quotation, "You can't get there from here," is something that I have heard for a long time. And as soon as I saw this, oh gee, the BGP routing stopped, I was like, you can't get there from here. And it's like, you're sitting there trying to figure out, well, how am I going to get there? And well, maybe you can go this way, maybe you can go that way. And then you realize, no, there's no path to get there. That's what it means when BGP stops working. Because BGP is this old Mainer basically sitting there talking to a bunch of other old Mainers, discussing the way that you should get your packets from point A to point B. And when it stops working, your packets stop flowing. Google engineering knew of the issue within 2 minutes. This is the amazing thing. 2 minutes. And this turned into a multi-hour outage. Tools didn't work. The debugging of the problem was significantly hampered by failure of tools competing over use of the now congested network. Remember that 33% packet loss? Well, guess what? Your tools that you're using in order to diagnose your broken network can't talk to anything on your broken network because your network's broken. You didn't put enough bullets in your foot, so you reloaded the gun and you put more holes into it. It's just the reality of the systems that we build. Great quotation from the original post. We have robust backup plans for handling the failure of such tools, but the use of these backup plans, including engineers traveling to secure facilities designed to withstand the most catastrophic failures and a reduction in priority of less critical network traffic classes, blah, blah, blah. Well, that just made us everything take longer. So can you imagine the stress of the people who are actually trying to fix this? Because, of course, senior management doesn't understand any of this stuff. They just simply know that they've got other senior management from their customers calling, going, excuse me, but WTF? Oops. It took them several hours to recover. This was another example of cascading failures. This is really, really, really common. Almost any time you look at complex systems that fail to work correctly, what you see is this cascading failure thing. Remember I mentioned the James Webb Telescope? The James Webb Space Telescope is absolutely amazing because in their deployment model, they had 384 independent points of failure where they could If any of those things had gone wrong, they had mitigations for some of them, but there were quite a few of them where if anything went wrong, you had a $10 billion piece of space junk. They managed to pull it off. And they managed to pull it off because they had spent decades simulating everything that could go wrong. And they still knew that there was the possibility that they'd get something wrong. All right. Today, like I said, it's going to be a little bit lighter. We're going to be talking about distributed logging. The basic idea of logging is tied into transactions. That's why I originally slotted this in after transactions. So I'm going to start by talking about transactions. Gosh, and I got to reuse a slide. Yes. My beautiful diagram, which I did in Illustrator, not in PowerPoint's crappy drawing thing. And I didn't do anything fancy. I didn't put drop shadows in there or any of the really cool whizzy stuff you can do with Illustrator. You can have 3D type and whatnot. Nope. And if you're really fancy, you can actually use Illustrator to do animation. But you got to have a lot of time to do that. Usually, you should figure about an hour per second of animation. It's time consuming. I mean, they have tools that will automate more of that as you get a larger amount going on. But I'm not that good. At any rate, transaction provides us with these guarantees. Remember, atomicity, consistency, isolation, durability. The big one there is really durability. Project 3 is about the durability guarantees that we're providing to our clients. That's why I went through that whole discussion of this is why you don't just simply take a random server out of the pool and say, okay, you can be primary now, because you would violate your own durability guarantees. When you're going to violate your guarantees, don't do it automatically. It's just asking for trouble. So again, acid properties, blah, blah, blah. Let's actually look at how we use logs then to implement our transactional systems. So one of the things that we started talking about, as I talked about, consistent cuts and the fact that we are looking for a path through the system that gives us the same outcome, and how different paths that yield the same outcome can be treated as if any one of those paths can be a stand-in. So the idea is these become linearizable. A log is naturally linearized because the order in which things happened is defined de facto by the log. Okay, well that's pretty easy to think about, but that's not distributed, is it? I have a log, I know what the order of the operations there were, but that doesn't tell me what the order of the operations in this log were relative to the operations in your log, or your log, or your log. So we use the same exact techniques, but now imagine we're doing this in my own log. I need to put some markers in there to say, this is what the state of the rest of the system was, so when I take all these logs and I start trying to analyze them, then I can reason about them. I can come up with a linearized path that gets me to the right state at the end. As long as it is a potential path that led to this outcome, I can use it. Same exact process. So when we start building distributed logs, there are basically two ways we can do this. We can either merge the logs at the time we have to merge them, or we can build a single big global log that does the merge on the fly. But in either case, what we end up with is something that we can linearize. And it's linearizability that allows us to do things like recovery. When things go wrong, we go back to our log and we recover from it. One of the things that's important here is we don't actually want an infinitely long log. This is in the real world we live in. So how do we keep that log from becoming infinitely long? You start a transaction, and you never actually commit it. Your log has to be long enough to have the start of the transaction in it. So you can't actually ever truncate your log there. So the first thing is you can't actually have transactions that are of arbitrary, unbounded length. You just have to decide. what's the maximum I'm going to allow? When I had to do this for the file system, what I basically did was I said, the way that I'm going to make my transaction log get smaller is I'm going to stop allowing more transactions to start and wait for the transactions to end. And we built a system that specifically said, transactions have to end before we can continue on. And if we stopped taking new transactions, our state space explodes. We stopped taking new transactions, then we knew that there was a bug in the system. So we impose an additional constraint that isn't in the general model because we had to make this work in the real world that we live in versus the beautiful, elegant world that the mathematicians live in. And I can't say anything bad about mathematicians. My undergrad degree is in math. So math is beautiful sometimes. And then sometimes it gives you results from beauty that you go, whoa, and you feel like you're on mushrooms or something. The axiom of choice is the one that always does that for me. Given any arbitrary set, you can define an ordering of the objects within that set. And then you go, okay, well, that makes perfect sense to me. Because you think of numbers, right? And then somebody comes along and gives you a proof using the axiom of choice that says, okay, well then here, given an arbitrary sphere, I can cut it up into pieces and make it arbitrarily large or small. Just using your axiom of choice. Neener, neener. You're like, wow. Okay, well, maybe that isn't obvious. So then you disallow the axiom of choice, and then a whole bunch of cool things go away, and you live in a much more impoverished world. That's the real world of mathematics. We don't live in that world. We don't have to deal with actual infinities here. We can talk about them when we're building our algorithms, but when we're actually implementing distributed systems, we are, fortunately or unfortunately, living in a finite universe, or close enough to finite that it's finite for us. We're living in this finite universe, and we get to constrain things. That will make our jobs easier. When we build logs, what we are trying to do is build a system that allows us to roll forwards or backwards to a consistent point in time. Again, this is one of these things, is that I'm sitting here working on the file system side. The other people that I'm all talking to are working on the distributed transaction processing side, and they're telling me, I'm learning this stuff and going, well, I don't have to worry about that problem. I can just make different choices. I can design it differently. I didn't allow a runtime abort. My transactions and abort meant that the system crashed. And I was undoing things because the system crashed, and all I had to do was get back to a consistent state so I could start running again. That's a really nice way of simplifying this problem. It's not general, but we don't have to always build the general solution. Building the general solution, especially in distributed systems, is often way harder than you're going to be able to achieve in your lifetime. So we have undo logs, redo logs, and then we have the combination, write-ahead logs, which combine undo and redo together. Interestingly enough, I actually finally went and dug up, and there's a link to it a little bit later, I dug up the reference that everybody gives to two-phase commit and transactional logs. And it is a tech report that was published by IBM in 1979, and I'm pretty sure that means that it was actually being practiced many years before that. And it was in turn included in a book that was published in 1980 that had a whole bunch of stuff about databases. And this is where all of the stuff I'm talking about at this level, it's actually spelled out. The log they describe is in fact what we would call a write-ahead log now. They have undo operations, they have redo operations, and they talk about the ordering of those. And I took captured one piece of one of the figures there. And you look at it and you go, this is actually really cool. And the thing I like about it is I sit down and I read an academic paper today, and these things are dense and chewy. You feel like you're chewing a piece of shoe leather. And then you go read something from the 70s, and it's like, wow, this is pretty straightforward. Because these people were just figuring this out, and they didn't have to put so much stuff in 12 pages to get it published. People just came along and say, hey, I got this really cool idea, and they'd write up, and it would make sense, and you could read it. It's kind of nice that way. And I was like, wow, this isn't a bad piece. It is actually closer to like 20 pages, but it's still not bad. And you read through it, and it's well written, and it explains in fairly clear language exactly what we're trying to accomplish here. But this is why we use logs. This is why we put transactions in logs. Because somebody sat down and said, this is the problem it solves. It gives us a way to go backwards or forwards to get to a consistent state. Logs provide us with this nice serialized version of events. I already said that, but you got to put it in writing too. And you pretty much have to repeat things 3 times before it will stick once. We can track distributed states, such as with a vector clock, to allow us to merge disjoint logs. Serialization doesn't have to be the order in which things actually happened. It just has to be an order in which they could have happened and yielded the same outcome. So we have potentially many different ways of getting there that are small differences in order that don't matter. That ordering is only flexible if it really does give us the same outcome. If it actually changes the outcome, then it's no longer a serialized order. Question in the back. Right, so one of the benefits of having, so the question is, what does this apply to? The outcome. One of the benefits of having a transaction is that the transaction, in fact, guarantees that it's the outcome of that transaction that matters. So we've created this quantized unit we can start reasoning about, versus looking at the universe of all possibilities and go, oh! It doesn't disclose the possibility that we have a bug in our transactional system. Because for decades, I've been saying transactional systems are easy to build and difficult to get right. And the reason for that is because if your transactions end up having subtle interdependencies, they're not really isolated from each other. You violated the isolation property there. So because we have isolation, yes, the only outcome we care about is that particular transaction. The moment that I have outcomes that bleed over between the transactions, I've violated my own ACID requirements. I don't have a valid transactional system anymore. So I guess that's the flip way to turn this around, is to say, and I did, if and only if, right? So yes. So there you go, there's the picture. That's actually out of the original IBM Tech report. It was really cool to look at this, because I've searched for this thing, and it took a little bit of digging to find it, and it was worth it. And I put a link to it, actually, because I put it on my my website. I mean, if they complain because, copyright violation or something, they can send me a letter. It's IBM. It would cost them way too much to have a lawyer actually track me down and send me a letter. Stop putting a tech report from 1979 on your blog. Okay. It introduces the idea of transaction logs, two-phase commit, and undo, redo, recovery. And this is literally the undo, redo picture. And it's like, wow, this is just great, You put a log record in when you actually do the operation, and then you run to the new state, and now you got that log record. Or you undo, you got the log record, and you go back to the old state from the new state. It's like it really captures, in essence, what this logging system is doing. And then, of course, we have, so this is the operation, and then this is, we have to unwind it, we have to roll it forward. I liked it. I just looked at that and I said, this is nice, and it's succinct, and it captures the idea of what we're doing with our logs, which is awesome. So in a write-ahead log, our goal is to use these undo and redo mechanisms to allow us to decouple the order in which we write things. I hadn't quite realized it, because I'd heard the term write-ahead log before, but I never really dug into it. The NetApp people built a file system called Waffle, the write-ahead log file system. And I finally got it. I was like, wait a minute, that's the same stuff that I did. I did a decade earlier. We just didn't get a really cool name like waffle, because half of building good academic papers is coming up with catchy sayings. So what do? You start a transaction, you write the old value into the log, you modify the data, you write the new value into the log, you commit the transaction, and now what you have is the old value and the new value. So if you have to unroll it, you can rewrite the old value, and if you have to roll forward, you can do the new, write the new value, and then you write that data to the disk. And what's actually cool is you can start writing data to the disk as long as you get the old value in the log first, written to disk. So there's some ordering constraints here, but you can reason about what has to be pinned down. And remember I was talking about how long transactions can run? Well, that becomes an interesting factor here, because the longer your transactions can run, the more important it is you be able to write things like your undo records, so you could recover from then writing the data itself out. And the reason that we might not want to keep all of that stuff in memory is because we don't necessarily have that much memory. We live in a modern world in which people run gigabytes of memory. I mean, my machine at home has 256 gigabytes of RAM, because you need that. I can run virtual machines on it. It's got 64 cores, so it's like I can throw 16 cores at a virtual machine and not even notice it when I'm playing games. This doesn't matter. But there's still a large number of systems where, in fact, memory is very scarce. One of the fun things about working at MSR was that I got to talk to a guy who worked on a project they had done where they had taken Linux and stripped it down so it could run in 16 megabytes. And then that takes me back to the days of learning to program. And the reason I remember this is because I'm doing some paper reviews for a computer education conference, and the first paper I picked up was absolutely excellent, and it talked about using the 6502, the Commodore 6502 processor, which is the same processor that was used in the original Apple computer, as a training aid for doing reverse engineering. And then they have a simulator for a VIC-20, and I'm like, damn, that's the first computer I programmed. It had 5K of memory, and 3.5K of it were used by the OS. What can you do with 1.5K of memory? So we do have situations where the memory is very constrained. When the memory becomes constrained, now I have to use storage space to act as an extension of that memory. So that ordering and being able to write things out can be the difference between building a system that works and not being able to build it at all. So that's why these kinds of things become important. If you're awash in memory, you don't care. You're not going to have to worry about this stuff. It only becomes an issue when you start getting resource constraints. But no matter how much memory we give you, no matter how many resources we give you, there's always going to be a point you hit those resource constraints. Always. Because no matter how much memory you give an application programmer, they'll want a little bit more. I'm a systems person. I know that application programmers have one reason of existence, and that is to make my life miserable. So, oh, you offered me a terabyte of memory. Well, I need 1.1 terabytes. I don't have 1.1 terabytes. Well, then you're going to have to simulate it. You gave me a 256 terabyte address space. I'm going to use it. And in case you don't know, the 256 terabyte address space is currently the maximum address space of the Intel processor architecture machines, where they have 4-level page tables and they can address 256 terabytes of memory. Now, what's fun is that, in fact, the entire address space, which is in theory 64 bits, which is 8 exabytes, 8 exabytes, and that's a number that, of course, you hear a lot. 8 exabytes. They only use a little tiny piece at the top and a little tiny piece at the bottom, and there's this big ass hole in the middle. So we can grow that address space. Intel's actually defined what it'll look like when they grow it to, 128 petabytes, I think. But they're not building any hardware yet, because we haven't actually run out of 256 terabytes of address space yet. but give Microsoft Word an opportunity and it will grow to fill all available space. Recovery is the process of taking that log and getting us back to a consistent state. Now, that can just be the transaction. I abort a transaction, I need to roll backwards on that transaction. There might be other transactional information in the log that doesn't apply to that transaction. I don't have to pay any attention to that because remember, I have the isolation property. I don't have to worry about what was going on those other transactions because they are isolated from my transaction. Isolation actually is hard because it's the thing that will rate limit us the most. Because you're in the middle of modifying something, I can't even look at it because I won't know whether to flip backwards or forwards based on the outcome of your transaction. So that's why we have this kind of mutual exclusion thing. And we will see there are ways that you can actually relax that a little bit. I've kind of talked about some of them, basically where you can have multiple potential values and your outcome can waver and depend upon what the other transaction's outcome was, and you need to know what those possible outcomes are. But that's what makes this stuff fun, is that you start with these very strong, rigid principles, and you go, well, but what if I was just a little bit sloppy here? What could I possibly do? And the reason we say, why would I want to do that, is because if I do strict lockout, it slows my performance. It serializes my execution. And that means I go slower. And sometimes we're willing to go fast and loose at the risk of extra complexity, or sometimes we're actually willing to at the risk of consistency. We're going to have this thing, I may have already mentioned this term, eventually consistent. The usual joke is that means never consistent. Eventually, in the fullness of time, we will reach a consistent state. And you remember I talked about that, about how we have these consistent cuts, but our rollback might be all the way back to the starting state. Well, okay, it's eventually consistent, yes, but it happens to be last year's eventual consistency, and that's done because it gives us better performance. We're not willing to do that for things that actually we care about. We do insist on something a little stronger than eventual consistency. Once a transaction has committed and all of the data mutations have been recorded to their correct location, we can remove that transaction from our log. That means that transaction can be truncated from the log. Of course, when we start interleaving these things, it practically means we're doing garbage collection. And the only thing worse than doing garbage collection in memory is doing garbage collection on disk. And I know this because my PhD supervisor here, her thesis was on garbage collection on disk. And this problem comes up over and over again. And when you explain it to that people, see, we disguise it. Again, it's labeling that matters. We call it cleaning in the file systems business. We clean our log. And what that really means is we garbage collect it. And that stuff I was doing at Microsoft Research was actually simulating what the cost of garbage collection was when you have massive amounts of storage and you experience read wearing. Each time you read from a piece of holographic storage, it degraded just a little bit. And the reason for that is because you banged a light through it, and that caused a small amount of scattering of the data that was actually recorded in the glass. And the craziest part, and this is the part that really plays with your head, the read wearing occurs before you've written the data. And you're like, what? Yeah. It was really weird. You literally could be in a situation where you had to stop reading from a zone of storage because you would be degrading it so much that you wouldn't be able to read the rest of the data off of it. So you'd end up in this panic situation. Go, okay, got to stop. Can't do any more reads. Can't do any more writes on this section. Got to move all that data over to a different segment. You have a question?
Actually from the law.
Okay, so the question was, Does it actually mean that once the transaction has committed and the mutations of the data have been persistently stored, you can get rid of the transaction? And the answer is yes. Because the only thing that transaction was trying to guarantee is you could get to that last state, which was, I made all the changes to the database. And they're recorded. Well, you can't get rid of a transaction until it has ended. So the point there is you don't need to store it in your log anymore. So you can clean that portion of the log up. See, I got to use the clean word. You can clean that section of the log up. And one of the reasons I picked Corfu is because Corfu actually uses a sparse log. And one of the motivations for using a sparse log is it gives you a model for cleaning up that looks like you have a great big huge virtual address space and you just start putting holes in it in the places you don't need anymore. And then you can garbage collect it underneath. And this is a very standard technique. In systems, we firmly believe that anything that's worth doing is worth doing through an indirection. I mean, I've been teaching operating systems for decades now, and seriously, at some point I had this epiphany, and I started teaching it to people. I'm like, why do anything directly when you can do it through a table lookup? And we do it all the time. So then you say, okay, let's talk about virtual memory. How many of you remember what virtual memory is? It's a table lookup. That's all it is. Instead of talking directly to the physical RAM, you go to a table that tells you how to take the virtual memory address and convert it to a physical memory address. And then you learn really screwy things like the fact that, hey, you can have different virtual mappings to the same physical memory. You can give your hardware devices their own customized view. What? Yes, devices can have their own virtual memory. And it can have nothing to do with the process's virtual memory. So you can have programs running, and you can have your busmaster DMA controller sitting out on your PCI Express bus, talking to the same physical memory using completely different mechanisms for doing table lookups. But that's all it is. It's a table lookup. And that's all the trick is in Corfu. It's a table lookup. And that's done specifically so we can simplify the cleaning of our log. Log compaction turns out to be a big deal. I'm sitting on a disk drive building a file system on this thing. My log compaction was I have to make sure that everything in it has been recorded so I can just recycle and reuse the space. Because it's infinitely long logically, but in fact physically, it's a fixed sized array of blocks on the disk. And I have one field in the header that says, oh, this is pass number n, this is pass n plus 1, this is pass n plus 2. You know how I actually tested the wrap condition? You were talking about testing techniques. This is just something I learned years and years ago. You pre-initialize it to just below the wrap point, so you always test the wraparound case. And that makes sure that your logic works correctly. Very simple trick, very powerful. Lots of people, I've seen so many people that just always initialize to 0. Like, but that's not the interesting case. The interesting case is when you initialize it to -1 and then it wraps to 0. Because of course we all know that -1 is just 1 1 1 1 1 1 1 1 in binary, right? All bits set. And the next thing that happens when you add 1 to that is, of course, it goes to 0, and of course there's that carry bit that we ignore. So it rolls back over to 0. Works great. It's a very simple technique. It works great. Use it a lot. Still do it. Always initialize things when code that I write. And what do I write in? I write in C. C doesn't give you any extra assistance. Oh, but you've got the standard library. Oh, yes. String handling in C. I do file systems, so all we do is lots of string handling. String handling in C is truly the tortures of the damned. But I can randomly poke memory values and do all sorts of crazy things with it, and I've been doing that for decades, and that's why we still write things in C, because it's small, simple, and it lets you do stupid things like, take those guns, line them up, and shoot your feet over and over again, and then ask yourself why it hurts. All right, truncation occurs when all the data changes in a given transaction have actually been recorded. Not in the log, but in the data itself. Truncation can and is often lazy. We don't have to reclaim that space aggressively. The Java garbage collector doesn't actively run every single time the state of memory changes. No, instead what it does is it waits until you're in some time critical function, and then it says, stop, I'm going to clean. And then it cleans everything. And then you come back in and you can't find anything. You know, it's like if you let somebody else clean your place, you can't find anything. If you've never experienced that, it's a lot of fun. All right, distributed logs. So now we actually have logs scattered all over the place. Question in the back. Yep. Think about why. In fact, if you do your undos after you do your redos, you may actually overwrite things that were done in the redos, because in a single transaction, you can do both, undos and redos. So if you did your undos after you did your redos, you'd essentially be rolling some of that state back to the beginning of time, and your redos would roll it forward. If you do all of your undos first, you roll it back in time, and then you do your redos, and that moves you forward in time. You don't want to interleave those two. At this level, what they were doing was storing values. But yes, even in operations, you need to make sure you compose the operations in the correct order. And the order in which they would have been composed is from the old state to the new state. You would never want to reverse those. You'd never want to do the change to the new state first and then apply the change back to the old state. You see why that would scramble things? I mean, I just put that on there because I learned that one decades ago, but I never see anybody actually explain that. Occasionally I'll read it. I have the benefit of having actually had to make every possible mistake with this stuff. That's my model of programming. I figure out all the ways to do it wrong, I try them, and then when I run out of ways to do it wrong, I finally just simply go, all right, fine, I'll do it right. You probably will feel that way about Project 3. Distributed logs. Lots of logs, scattered all over the place. The simplest and the most traditional way of doing this is that we have at least one log that defines the outcome of a given transaction when we start building our distributed transactions. Of course, there's that interesting little problem, which is one log becomes a single point of failure, and so one of the earliest solutions to this was, well, we'll just simply use chain replication. I think that's actually what they described in the IBM Tech report, was chain replication, because they're concerned about that kind of failure. The primary backup project, Project 3, is really a super simple implementation of chain replication. Logically, that's what we are doing. The primary does it, gets an acknowledgement from the secondary, and then acknowledges it back to the client. And that's how we keep things in sync. So it's a chain of length 2, or 1, depending on whether they're 0 or 1 indexed. It's a chain of length 2, and therefore is as minimally expensive as you can get with chain replication. We'll see that we can make it way more complicated and more robust and able to handle more classes of failure. In these real-world distributed systems, what we see is 3. So we'll have one of our replicas will be someplace else in the same data center, and the other replica will be someplace else in a different data center. That's a very common, simple technique for doing that. And they won't necessarily even chain it. They'll send the messages to both and then wait for both of them to acknowledge and then proceed. Project 3 is not that complicated. We're going to jump from Project 3 to Project 4, where we're going to give you Paxos. And the magic number in Paxos is, in fact, at least 3. We tend to like odd numbers. Okay, so this thing that makes the decision, the outcome, I've mentioned this before. We're going to call that the coordinator here. There are lots of things you can call it. The leader, the coordinator, what else have I heard it called? I don't know, you can call it whatever you want. It does the same thing, which is it records the outcome of a given transaction. It creates a transaction identifier that ties related transactions together across the different logs. Because remember, now we have multiple logs. Now we're trying to look at the distributed log problem. It knows all the participants in the transaction. It provides the atomic commit. How does it do that? It has its own log. Now it just looks like the local case where we had just a local transactional system, except now we have stuff linked in there. And the logs are used to determine the outcome if we need to recover, if we need to abort a transaction, or if we need to roll it forward. This is tied into this whole idea of two-phase commit. So a local log, and we're going to just by extension move this into distributed logs. We have a transaction that we start, and then we either commit the transaction or we abort the transaction. There can be information between the begin and the commit that gets recorded in the log as well. But in fact, when it's just the outcome of the transaction that matters, I don't need to have that other state. I can build a more complex model where I combine some other stuff that I'm keeping track of too. But this is the minimal set that I need as a coordinator. Now, when I'm talking to the nodes that are participating, eventually one of the nodes is going to say, all right, I'm done. This is what I usually think of as the client. So whoever started the transaction wants the transaction to end now, and it says, yo, coordinator, I'm done. I've mutated all the state that I need to mutate. And then the coordinator says to all of the nodes that are participating in that transaction, it doesn't have to send it to all the nodes in the world, only the ones that are participating. Okay, please let me know if you are ready to commit. Once all of the nodes have acknowledged that they are either prepared to commit or any of them has said, no, I'm not, I'm going to abort, the coordinator has the information now to make a decision in the outcome. In some ways, this is a form of consensus. It is unanimous consensus. Everyone agrees or everyone disagrees. Even if you agreed, well, sorry, somebody else blackballed it. And thus we have a decision. And that's really all we care about. Ultimately, in consensus, we just need to make sure we all come to the same decision. So everyone agrees that it rolled forward, or everyone agrees it rolled backwards. There's no in-between here. Of course, what makes this hard is that we're going to have to deal with the failure cases. So, nice little picture, shows you a good walkthrough here. Actually, it was really fun. I'm looking around for pictures to borrow, and this was Don Acton's slides from 2014. And I was like, this is actually better than what Ivan had, I think. Like, cool. So, in the voting phase, we start that because the node sends a request to commit. And the coordinator then sends the prepare out to everybody. And then all of the nodes do whatever they need to do to be ready to roll the transaction, to commit the transaction. And so here I have the coordinator in the middle, the orange circle, and then I have the nodes. So I have the node on the left, which said, okay, I want to commit this transaction. And then he sends to all of the nodes. I mean, he doesn't have to send it back to the node that asked. He sends it to the nodes that didn't ask. And he says, okay, are you prepared to commit? And once they say they are prepared, actually he does send it in this picture. Okay, fine. You can make it either way. Once they do say they're prepared to commit, then he makes the decision. He says, okay, everybody has said that they're in favor of committing this. I've made a decision. Our consensus is it's committed. And you can see that when we look at the individual logs, what ties them together is that transaction ID. The state, the information, the things that are going on in the individual transactions can be different. I have two databases. I made a mutation here. I took it out of the inventory database and I put it in the to ship database. So I'm mutating different data in different databases, but I'm tying them together because they are actually against the same transaction. Once the transaction is complete and the coordinator has answers from everybody, it then commits it to its own local log. So it writes begin here, it writes the commit here. And then the coordinator tells everybody that the transaction committed. Now, in the common case, this is what normally just It just works. It just happens. And this is optimized for performance. That's why I said I probably wouldn't, if I were building this protocol, I probably wouldn't call back to do a prepare to commit to the guy who asked me to commit. I would assume that meant he was prepared to commit. That would have just been a small optimization, one fewer messages, blah, blah, blah. It doesn't matter. What does matter is that this is the normal case. Everybody's alive. Nothing needs to be recovered. Sometimes things go wrong. Remember the FLP theorem and the whole fact that we basically, as long as we allowed arbitrarily long message delay, we couldn't actually reason about the system. So the way that we really got around this was we said, okay, well, we'll just use timeouts. And it's going to be my relative timeout. This is a real world kind of compromise. There are going to be times when the message gets to us after our timeout. Too bad. We need to be able to provide guarantees. And this is how we're going to provide those guarantees, even if they're not 100% correct. So the coordinator uses a timeout mechanism. If a node does not respond within the timeout window, we abort the pending transaction. In project 3, there was this whole interesting conversation about the ping timeout timer. And the fact that, and then it wasn't until I really looked at the timers and I was going, oh, so a ping is supposed to go every 25 milliseconds and a timeout happens every 100 milliseconds. It's like, okay, so what I basically said is if I haven't heard from you in 4 ping times, I'm going to say you're dead. And I'm like, okay, is that the right number? Well, in a simulator, it's perfect because we know that the actual time to send those messages is 0 or very close to 0. In a real network, maybe 100 milliseconds is the right time, but maybe these are geolocated apart from each other, and 100 milliseconds isn't quite enough for me to be comfortable. Maybe I make that timeout a second, and I wait 10 times, so I expect you to send one every 100 milliseconds. There's a balance between how often I send these pings and how much bandwidth, how much network activity I'm generating or churning. And if I have 1 million of these things and everybody's pinging everybody else every 5 nanoseconds, then all my network's going to be doing is sending ping messages, and I'm not going to get any work done. All right, so in the case of an abort, the nodes will have to recover their log. On the coordinate, let's see. So when we have a log recovery going on, that we have a transaction. Okay, so let's suppose I'm the node and I'm the one who crashed. I come back up, I look at my log. I realize that I started a transaction here and I don't have a prepare to commit in the log. Therefore, I know that the coordinator, it's been too long. I died long enough that the ping timer expired. The coordinator would have declared that I'm dead. That means I know the transaction aborted. Maybe that time is really long, in which case then I would still have to treat it like, no, because I haven't answered. I know I haven't answered. So I might need to talk to the coordinator. Maybe I could recover from that case, but we're going to ignore that. Let's walk through this. The time has expired. I know I didn't say that I was ready to commit this thing, so I know what the outcome of the transaction was. It aborted, so I can just unroll the transaction. That makes my recovery easier to reason about. If I have a log that indicates that I did do a prepare to commit, then I have to ask the coordinator what the outcome of it was. Hey, what happened? So there has to be a mechanism for the node to ask the coordinator, what was the outcome of that transaction? But what if the coordinator is unavailable? I have to wait. This is recovery. This is actual recovery after a node failed. We can truncate them, yes. Right. Okay. Yes. That's an excellent question. So the question was, how can the coordinator know when the node is going to come back and ask this question? It's a great question. How would you solve it? See, this is an interesting thing, is that the coordinator might provide different cleanup semantics than a node might. It's easier to reason about what the node can do. Once the node knows that the transaction committed, it can immediately truncate that. But the coordinator might not have that ability to do that. And so what you're going to end up doing is the same thing that we did with the ping timer, which is you're going to make an arbitrary choice here. And you're going to say, okay, I'm willing to store this for the next week. If you ask me about a transaction that happened more than a week ago, I'm going to not have an answer. And now you're going to have to reason about how do I handle that on the nodes side of things. So what I probably would do in that instance, let's see. I probably would use the fact that everybody told me they committed as the mechanism for knowing what I could safely clean up. That would be a reasonable intermediate rather than just simply choosing an arbitrary time cutoff. And now he's gonna make me go back and look at that previous slide. So I don't show you any message from the node saying thank you. If I added a message that said thank you, then I just wait until I get all the thank yous, and then I would know that everybody had rolled forward, and I don't have to keep that in state anymore. So given that problem, I can now solve it. But of course, given the initial description, let's just assume you never throw those logs away. And that's probably good enough for a student project. It's not good enough for the real world. You're absolutely right. And you're going to have to reason about that. Great question. So I actually thought I was going to finish this one on time, if not early, and I've managed to pretty much run myself out of time anyway. Probably it must have been the Vogon poetry at the beginning that puts everybody to sleep. They make a big deal out of Vogon poetry in Hitchhiker's Guide. It's pretty funny. So I will. I'll do my usual thing, which is go back and stand in front of my computer at home and record the last 10 or 15 minutes. Because then you guys can't ask questions. And I will see everybody on Thursday. Thursday, we will actually start talking about consensus algorithms. We'll be talking about quorum replication, which was one of the earliest consensus algorithms, dates from about 1980. And I'll throw a little bit of interesting stuff in there because there's this interesting theory paper from the 90s that talks about quorum replication that you can perform with less than a majority. So Gifford did majority quorum replication, and then these cool theorists said, well, actually, if you organize things in this matrix, you can do it with less than a majority, which is it's a very interesting outcome. So I'll see everybody on Thursday.